Okay.
So hello everyone. Thank you for joining in this weekly research seminar. Today we have Dr. Hang Dai, who will present his work titled The Dream of Autonomous Vehicles. Dr. Hang Dai is currently working as an assistant professor at Mohammed bin Zayed University of Artificial Intelligence. He received his PhD degree from the Department of Computer Science at the University of York, UK in 2018. He was an overseas research scholar with the University of York from 2015 to 2018. He has published over 30 conference papers, journal articles, and book contributions. He served as a reviewer of NIPS, ICCV, CVPR, ACCV, ICML, and ICLR, and a program committee member of AAAI and IGCI conferences. His research interests include autonomous driving, 3D deep learning, and 3D computer vision. If you have any questions during the talk, you can always type in the question and answer tab or ask at the end of the talk. Dr. Hangdai, the floor is yours. Thank you.
Thank you, Dr. Harris, for introduction. Today, the topic of the talk is about the dream of the autonomous vehicle. Here is a brief introduction of me. So the first question would be, why do we need a self-driving car? So each year, 1.35 million people are killed on roadways around the world. Every day, almost just 3,700 people are killed globally in road traffic crashes involving cars, buses, motorcycles, bicycles, trucks, or pedestrians. And self-driving cars have huge potentials to save lives from traffic accidents. Another reason is like there's too much traffic. So the time spent on commuting could be time spent doing what you want to do. And also it can save people from a long distance driving. So you can sleep when the autonomous driving car just drive you to the destination. Also, some people may not be able to drive. Aging or visually impaired ones can also use a self-driving car to travel around. They wouldn't have to give up their independence. So about the level of the automation in autonomous driving car. So level 0, driver is continuous in control of speed and direction. That's what we usually do when driving a car. So there is no active intervening vehicle system assembled in the car. Level 1, driver continuously performs the longitudinal and lateral dynamic driving task. Some other driving tasks are performed by the system. For example, the park assist. Level 2 is a partial automation driving mode. Driver must always monitor the dynamic driving task and the driving environment. And the intervening vehicle system can perform driving task in a defined use case. For example, traffic jam assistance. This partial automation driving system is widely used as the intelligence system in the cars nowadays. Level 3 is a conditional automation mode. The driver doesn't have to always monitor either the dynamic driving task or the driving environment, but the driver must always be in a position to resume the control of the car. The system performs the lateral driving task in a defined use case, recognize its performance limits, and requires the driver to resume the dynamic driving task with sufficient time margin. Highway patrolling is a good user case of the level 3 autonomous driving. Level 4 autonomous driving has a high automation. The driver is not required during the defined use case. The system takes full control of the driving a car in a defined use case. For example, urban automated driving. Many autonomous driving companies endeavor to deploy the level 4 autonomous driving systems. This video shows a test of the level 4 autonomous driving in urban environment. The person sitting there in a safety is a safety staff who needs a safety and testing license when testing an autonomous driving car. This is requested since the car is tested in a real-world environment. And you can see the monitor in the car shows the 3D perceiving information surrounding the car. And level 4 autonomous driving is of full automation. The system takes fully control of the car in all situations during the entire journey. So no driver is required. It is a dream of autonomous driving. That's what the industry companies and researchers in autonomous driving research field want to achieve in the end. So experiments have been conducted on autonomous driving system since at least the 1920s. Trials begin in the 1950s. The first semi-automated car was developed in 1977 in Japan, which required specially marked streets that were interpreted by 2 cameras on the vehicle and an analog computer. The vehicle reached speed up to 30 kilometers per hour with the support of an elevator rail. A landmark autonomous car appeared in the 1980s with Carnegie Mellon University's Navy Lab and ALV project funded by the United States Defense Advanced Research Project Agency starting in 1984, and the Mercedes-Benz and BUMEP project in 1987. By 1985, the ALV have demonstrated self-driving speed on 2 lines roads of 31 kilometers per hour with obstacle avoidance added in 1986 and off-road driving in day and nighttime conditions by 1987. So at the starting point of self-driving, the system needs to be clear about the accurate position of the car. To achieve that, the system processes both the map and the sensor information to determine the location of the car. So which street and which line. The system needs to be aware of the surrounding objects. This is to detect and classify objects all around the car based on their size, shape, and movement pattern. These functions are corresponding to the 2D or 3D object detection and object tracking tasks in computer vision and machine learning. When the system is clear about the surrounding environment, one step further, it should be able to predict what all objects around the car might do next according to their movement pattern. Finally, the system can choose a safe speed and the trajectory for the car when considering all the information connected, such as the object's location, movement pattern, a predicted future movement, traffic lights, and so on and so forth. This is a proof story of the self-driving car. To show a detailed picture of autonomous driving, we can take a close look at the decision and control architecture. From our everyday driving experience, we know that the decision in driving must be made in a very short time, accurate and swift. So how can we control the self-driving car actions in a dynamic world under strong real-time constraints? We can combine and adapt the independent functions to sense the environment using various sensors. There are many sensors and units assembled in a self-driving car, including Lidar sensor that creates a 360-degree 3D map of the vehicle surroundings using lasers. Cameras that can focus near and far to detect vehicle activity and also the pedestrians and the traffic signs. Stereo cameras that help detect objects, and a global navigational satellite system, a GNSS that provides GPS positioning, and radar sensors that use the burst of the sound and to determine the distance between objects. So we also combine and adapt the independent functions to interpret the dynamic things using semantics and prior knowledge. It can also be used for planning the car motions and deciding the most appropriate actions to be executed by the car. And also we can combine and adapt the independent functions for acting and interacting in the real world. And this is about how to control self-driving car actions in the dynamic world under strong real-time constraints. As demonstrated, the perceiving system is very important in decision and control architecture. The objective of the perceiving system is to perceive what is happening in the dynamic sense using various sensors. Lidar sensor is one of the most important sensors assembled in the autonomous vehicle. And in the video, you can see that
you might have noticed a rotating device installed on top of this autonomous vehicle. Sometimes these devices are mounted on the bonnet. This device is called Lidar. It acts as the eye of the self-driving vehicle, providing a 360-degree view of its surroundings in order to enable safe driving. Continuously rotating Lidar system sends thousands of laser pulses every second. These pulses collide with the various objects around the vehicle and reflect back the signals. These light reflections are then used to create a 3D point cloud. An onboard computer records each laser's reflection point and translates this rapidly updating point cloud into an animated 3D representation. The 3D representation is created by measuring the speed of light and the distance covered by it, which helps to determine the vehicle's position with respect to the objects surrounding it. The 3D representation also monitors the distance between the vehicles that pass by and any other vehicle in front. It also helps to command the brakes in order to slow down or stop the vehicle. When the road ahead is clear, it can also allow the vehicle to speed up.
So the main difficulties include the huge homogeneous sensor data and the sensoring error, uncertainty, and the demanding of the real-time processing. And the main functions include the localization and mapping, objective detection, checking, and static obstacles. Another function unit in decision and control architecture is sense understanding. That is to understand the content of the dynamic things using contextual and semantic knowledge. In this video, it shows a highly dense semantic segmentation results for video captured by the camera assembled in car. And different colors indicate different object classes. And the main difficulties also include uncertainty, real-time processing, and reasoning about the various types of knowledge. And the main function includes the decision detection, checking of objects, object classification, prediction, and risk assessment. The decision-making function is to plan car's motions and decide the most appropriate action to be executed by the car. Decision-making in dense traffic scenarios is challenging for automated vehicles due to the potentially static behaviors of other traffic participants and the perception uncertainties, for example, checking noise and prediction errors. And this video shows an animation of the decision-make platform. And the main difficulties include online motion planning under various constraints and decision-making under uncertainty using contextual data. And the human-aware motion is to control the car to execute safe and acceptable interaction with passenger. The video shows an example of the interaction between passenger and the autonomous vehicle. It is called Mount for Autonomous Vehicle, C4AV. And here is an example mount. Okay, so sometimes the passenger sees a friend maybe walking nearby, and the passenger may want to give a command that requires the autonomous car to stop near he or her friends. So that's the kind of the motivation of this kind of interaction between the passenger and the autonomous vehicle. And in the following slides, I want to introduce some interesting observations in the research of autonomous driving. So the first is about trend in Germany and testing in the USA. The past few years have been a flurry of interest on the problem of 3D object detection, resulting in large gains in accuracy on the Kitty benchmark. However, in the excitement this has gathered, it has been often forgotten that Kitty is a dataset abundant from a narrow domain. It was connected using a fixed sensing apertures by driving through a middle-sized German city and the German countryside in clear weather and during the day. Carrying these bounds over to a new environment in a different part of the world might cause the object detector to miss cars or pedestrians with devastating consequences. So there is an interesting investigation called Trend in Germany and tested in the USA. That is, train a deep learning model in a dataset connected in Germany and test the trend model in another dataset connected in the USA. We can see that when train and test in the same dataset, the in-domain results are the best compared with the other training and testing setting. This is caused by the domain shift when training in one dataset and testing in another. So how can we overcome this domain shift? There are two approaches to do the domain adaptation. The first one is a few-shot fine-tuning. It is to fine-tune the already trained object detector with a few-shot examples. The few-shot fine-tuning still requires training. While the second approach modifies the already trained object detector so that its predicted box sizes can better match its target statistics. For example, the average height, width, and length of the car. In other words, it just needs to modify the output bounding boxes according to the target statistics in the testing dataset. As can be seen in the image below, in some region of the world, the road is narrow and the short car, for example, the two-door vehicles, are very popular. While in some region of the world, people always love large cars like four-door cars, SUV, so on and so forth. When you train a model in a dataset connected in the formal condition and testing model in a dataset connected in the latter condition, statistic normalization is a good way to do the domain adaptation without additional training. Let's see the results. Do not be overwhelmed by this large table. Just look at the columns in green boxes. Surprisingly, the non-training measure statistic normalization (SN) achieves significant improvement. A few shot FS fine-tuning, the training measures also achieve performance improvements. Without this kind of investigation, we never know that a simple modification of the output bounding boxes according to the target statistic can achieve such significant improvements. Another interesting problem is about the debate between the Lidar-based and the vision-only-based perceiving system. And the image below shows what sensors are assembled in a car for a Lidar-based perceiving system. And for the vision-only-based perceiving system, the Lidar sensor and the FG maps are removed from the previous version. So that's the main difference. To know why we need or don't need Lidar sensor, we need to know the mechanism of the Lidar sensor. As shown in the image, the Lidar is measured for determining the ranges by targeting an object with a laser and measuring the time for the reflected light to return to the receiver. It is a direct way to perceive the 3D view world. And there are many types of Lidar sensors that deal with different range of distance. How about vision-only-based approaches? The vision-only-based approaches uses stereo camera or sequence of cameras to cover the vision field for computing the 3D information from the motion difference among multi-views. So it is an indirect way to perceive the 3D information. So why do some companies still stick to the vision-only-based systems? Maybe because of the cost of the Lidar sensor. It's very expensive. But as you know, nowadays, many companies are also trying to manufacture the cheap Lidar sensor and reduce the cost of the Lidar sensor, like some company called Huawei or DJI that creates some low costage Lidar sensor for autonomous vehicles. And Lidar sensor may not be robust in complicated weather conditions. For example, heavy rain may cause noisy data and inaccurate measurement. This kind of problem, I think, it also can be resolved with the development of the Lidar sensor, because currently there are also many research teams and companies working on this problem and resolve this issue. And also, these people believe that the vision-only based system has the comparable performance in 3D perceiving. But for this, is it true? And also with the development of the low cost and also robust LiDAR sensor. So why do we abandon the LiDAR sensor when we want to achieve the dream of the autonomous vehicle? So let's see the vision only for autonomous driving. So from a research perspective, I take some examples. 4 examples. One is about the depth from the monocular image and stereo matching and 3D object detection for monocular image and the 3D object detection for stereo images. First, I want to introduce the KITTI benchmark, which all these methods test on. The tasks include stereo, optical flow, 3D object detection, and the 3D tracking, so on and so forth. Accurate ground truth is provided by the LiDAR sensor and the GPS localization system. Up to 50 cars and 30 pedestrians are visible per image. And KITTI is a mostly widely used autonomous driving benchmark. And most of the latest research work in autonomous driving are tested on this benchmark. So this flowchart shows the top measure about depth prediction from monocular image in KITTI leaderboard. Look at the input and the output. The RGB image is captured from the camera assembled in car, and the output depths need to be supervised by the ground truth depths. And the ground truth depth is usually gathered by the point cloud data captured from the LiDAR sensor. And the flowchart here shows the top measure called about the stereo matching in KITTI leaderboard. The input are a pair of image from the stereo camera, and the output is also supervised by the disparity map that is generated from the point cloud data captured from the 3D sensor. That means when vision-only based perceiving system want to perceive the 3D information, it still requires 3D ground truths that are from the LiDAR sensor or the 3D scanning sensor to supervise the learning process. So you can achieve better performance than the learning without the 3D ground truth supervision. How about the performance gap between the two systems, vision-based and the LiDAR-based? Let's take the 3D object detection from monocular image as an example. The input is a single image from monocular camera. The output 3D bounding boxes are supervised by the ground truth boxes annotated in the point cloud that is captured from the LiDAR sensor. Even with that, researchers still need to carefully design some module. For example, this extrinsic vibration block as shown in this flowchart to perceive the 3D information. How about the performance? MONA EF is the best measured in monocular 3D object detection. However, compared with the methods that directly use the point cloud data for training, there is a huge difference among them. Again, this is best measured on the 3D object detection for stereo images. It's called pseudo LiDAR++. In this method, it predicts a depth map to compute the point cloud data as a pseudo LiDAR data before doing the 3D object detection. As demonstrated in previous slides, the depth prediction network from the stereo image still relies on the point cloud data from LiDAR sensor. And the prediction cannot surpass the quality of the point cloud data directly collected from the LiDAR sensor. So look at the performance. Even though the pseudo Lidar plus has large performance improvements against the monocular-based methods, it still has a large performance gap between the stereo camera-based method and the point cloud-based method. So back to the questions. So is it true? So the performance gap between the LiDAR-based methods and the vision-only based methods are still huge. So why? Because LiDAR sensor can provide an accurate 3D information that can be used as the ground truth for training in the vision-only based methods. So when you use this ground truth, how you can be that ground truth in the following downstream tasks? So with the development of the cheaper and more robust LiDAR sensor, if we can get accurate 3D information directly from the LiDAR, why do we abandon the LiDAR sensor when we want to achieve the level 5 autonomous driving? So something like the vision-based autonomous driving research, the value is low or not. I think it depends on the applications, because the applications can for now or for the future. And this video shows a technique that people can attach a camera and a screen under the back mirror. It can detect the road condition and show you the guidance of the routine using AR, and give you warning when the car is too close to your car. And this kind of 3D information, I mean the distance, can be captured by the vision-based 3D object detection method to know the 3D location of the frontal cars. So it's still the human who drives the car with the assistance from a 2D camera system. And also for this kind of vision-only based methods, it can be applied, directly to the mobile phone applications, and use the camera, a mobile phone camera, to do the 3D object detection, semantic segmentation, and reasoning things, and just to assist the driver in when they driving in a complicated condition in the highway. And this shows the latest research progress in my group about the monocular 3D object detection. So this shows the architecture of the monocular 3D single stage object detector. And the backbone of this network is modified from the DLA 102, and they include a two-stage feature alignment, and a classification head, and 2D and 3D center regression head, and also a asymmetric non-local block, especially designed for the to predict the depths. So this kind of module just to improve the 3D perceiving capability in the network. And others are the regression heads, 2D box regression and the 3D box regression. And this shows the performance improvement about on the monocular 3D object detection. And this is about the LiDAR-based point cloud data for a 3D single stage object detector. And this work is assembled with a mask-guided attention, so it can guide its network to learn and to more focused on the objects of interest. And the results on the left shows that how the attention works and focus and forcing the learning to focus on the vehicle part. And the table on the right shows the performance comparisons on the Waymo dataset. And Waymo dataset is the latest dataset and the largest one in autonomous driving. And this work is also a 3D object detection for point clouds. And it is carefully designed with a voxel to point cloud decoder. So in the backbone, first we project the 3D point cloud to the voxel-based feature extraction, and then when we want to have dense information from the BEV feature map, we need to have a voxel to point decoder to decode the dense information from the BEV feature map. And this design, as you know, without a point cloud-based encoder, so it's a more simplified design. And in the voxel to point the decoder here, and we have a point cloud segmentation guidance to guide the feature learning. So the feature is enhanced for the 3D box prediction. And the images on the left shows the detection results, the visualization results, and also the kind of the segmentation, point cloud segmentation results inside the bounding box. Also, in the table, it shows the performance comparison on the Waymo open dataset. Another interesting topic in the autonomous driving, as I said, it's an interaction between the autonomous car and the passenger. So the task is called talk to car. Talk to car aims to tackle the joint understanding of the vision and the language learning under a real world task setting. And in the example command, the command 1, and you can see that it's a green light, right? The car should go passing the street, but there is a man going to pass. So we can give a command like this, and the system detects the person, and then the car can do some actions accordingly. And for the second example, you can see a car in front. They stopped in the line. So you can give a command like move to the left line to avoid the stalled car. So you will recognize the referred object, and then the car can do the following action to move to the left line. And this is a measure we propose to tackle the joint understanding of the vision information and the language information. So it's a transformer-based method. It has a transformer encoder to encode the command information, and have a CAN to extract the image information, the vision information. And these two modality of information are aggregated in the transformer decoder, and then we can find the specific object that the command referred to. And inside the transformer encode, this is the detailed design. So each in the encoder, they have 6 layers of this kind of multi-head attention design. And in the encoder, in the decoder, it also has a 6 layer of multi-head attention design. And this is the performance we achieved in the challenge. And you can see that it achieves a significant improvement against the existing method. So one step further, we use a global vision linguistic BERT model to aggregate the the language information and the image information in a global BERT model, rather than just a encoder and a decoder based transformer. And we carefully designed the input architecture, like the token embedding, the visual feature embedding, the segment embedding, and the sequence embedding. And with this carefully designed data structure, and these two modality of information can be well aggregated in the global BERT model. And also with the advancement of the pre-training strategy, and our model achieved the first place in the command for autonomous driving autonomous vehicle challenge in the CCV 2020. And that's which achieved the first place and the second place in that challenge. So this is the end of the tutorial on the autonomous vehicles. Thank you for your listening. So is there any questions? Let's see. So one question it asks, do you think that the vision-only system can be very vulnerable to adverse attacks? Yes, I think you are correct. Even not just in the 3D object detection, like the 2D object detection, it also can be fooled by the advisory attacks. So so like I said, this kind of system currently, I think, for the application, it can be just used for the assistance. It cannot be cannot be directly used for the high level autonomous driving systems. Yeah. I don't know if this answers your questions or not. Yeah. So no more questions come from the audience. Okay, Harris. Okay, I think one more question has come from the audience. It's kind of typing something there. Okay. So what do you think about using external microphones as sensors to be used in autonomous driving, since human use hearing? Yeah, this is a very good question. Actually, in the latest research, people use this kind of information to to guide autonomous vehicle cars to do actions, because sometimes they may people just make some noise or a some sign language like the light, the left light or the right light when you want to change the line. Some people will turn on the light, right? And this kind of information and also the sound information can be used to guide the autonomous cars to do to do the decision and following actions. And also, I think there is a public data set called command for navigation or something like that. So it's kind of you also can give some commands for the car to do the navigation kind of task. Okay. One more questions. Do you think that a monocular 3D vision problem is a very ear-posed problem, and the accessory data like Lidar is absolutely necessary? And in that context, why some company still go for vision-only system? So first, like I said, and like I demonstrated in the slides, the molecular 3D vision, this kind of research or the applications, they still have some, the real application values. It can be used as an assistance in the driving, but it cannot as a a very confident information to guide the car to do some decision and following actions. And the LiDAR sensor is absolutely necessary or not. From my point of view, I think the LiDAR sensor is absolutely necessary, because when you follow the latest development of the LiDAR sensor, and you know that many companies are working on to manufacture the cheap LiDAR sensor and also robust LiDAR sensor. And I think in the near future, we can have a very cheap and robust LiDAR sensor that be totally fine to be assembled in an autonomous driving car. Why some company still go for the vision-only systems? So the reasons I showed in the talk. So there are three reasons I showed in the talk. First is about the cost of the LiDAR sensor, because it's very expensive, and also the previous version of the LiDAR sensor is very vulnerable because it will produce the laser light, and this kind of device need to be changed timely. But I think this now is improved, and also the cost of the LiDAR sensor becomes cheaper and cheaper. And also, the LiDAR sensor may not be robust in the complicated weather conditions. For example, the heavy rain may cause the noisy data and inaccurate measurement. And this, I think, is now being resolved and with more robust LiDAR sensor. And more importantly, the most important reason is these people believe that the vision-only based system has a comparable performance in 3D perceiving. So that's, I think, when they start this, start from the vision-only based system, and they believe that this can beat the LiDAR-based method. So they just stick to that way and to the end. Yeah, I think that's what they probably the reason behind this. Yeah.
Thank you, Dr. Dai. This is Mohammed Yaqub here. So I'll take care of after Harris. I think Harris has a problem. So if
Okay.
I may ask a question as well on the between car communication, you know, like we were talking about 5G, and 5G hopefully will allow us to transfer data between different points. So what do you think is needed? What sort of, where's the research heading to allow more into between transferring information between cars and making decisions between cars collectively?
Okay, thank you for your question. It's a very good question. That's the part is not covered in this talk. It's related to the 5G things. It's called vehicle to X system. So it's kind of so in the future, imagine that all the cars are autonomous vehicles, and they are assembled with the 5G or high speed network. And these cars can share information internally, so they can do some decision ahead. So when you for example in the interaction street, and there's too much traffic, and the car stopping there, and the autonomous car there already know that there is a traffic jam, and this information can go to the car which is running ahead towards this street, so you can get rid of that, something like this. So it's kind of in the future, the car also have this kind of interaction, and also this information, this actual information, and this interaction definitely helps the autonomous vehicle to make better decision and the following actions.
Thank you. If I may ask one more question. So
Okay.
at the end of the talk, you focused into, you spoke about the BERT models and transformers, which is gaining a lot of interest in the vision and non-vision, previously non-vision, but now more in the vision domain as well. So with the use of vision transformer, we know these sort of methods are sort of like heavy to use, and they're complex.
Yeah.
And
Yeah.
what do you think is needed to allow them to be more light and more usable in this domain?
I think with the development of the transformer, I think the researcher will simplify the architecture of the transformer. You know, I think the latest research in the transformer shows that the feedforward layer is kind of a redundant layer in the transformer-based model. So kind of they remove this feedforward layer, and the model can also achieve a good performance in image classification, object detection, and semantic segmentation, this kind of downstream tasks. So I think at the beginning, we focus on this kind of multi-head attention to achieve a good performance in the vision-based task. And later, I think we're more focused on how to achieve real-time processing with the images of 3D data, this kind of thing. Yeah.
Thank you. And maybe I'll end with one more question, maybe outside the scope of autonomous driving, but on the transformer. So what are your thoughts on, is this the end of a long era for CNNs, and the transformer will just be the solution for many of these vision problems, or do you think there will be other solutions which combine both of them?
I don't think it's the end of the CNN, because currently I think the transformer-based methods kind of meet a bottleneck of the performance gains, and people just want to I think the CNN, the convolution-based methods, still have the advantages in the vision-based the vision tasks. So the combination of the convolution and the transformer layers maybe can be a future direction in the vision tasks. Yeah.
Okay. So I guess that's it for the question. I think you answered the question in the Q&A, the last one, Dr. Dai. Is that correct?
Yes,
Yeah.
I think it's
Okay.
done. Yeah.
So thank you very much for all of that. I would like to finish up with thanking you for your fantastic talk and your thoughts, and thank everyone for attending. Thanks a lot.
Thank you. Bye.
Thank you. Bye-bye.